Welcome to this lesson where I want to provide a quick foundation into encryption. Now I want to keep foundation lessons as short as possible, so let's jump in and get started. Before we get started though, I just want to cover the topics that we're going to go through in this lesson. I'll be starting by talking about the different approaches to encryption, so encryption at rest and encryption in transit. I'll follow up by talking about the different concepts, so the different components and how those fit together. I'll cover symmetric encryption, asymmetric encryption, including the differences between those two, and I'll finish up the lesson talking about signing and then steganography. Now I'll get started by talking about the different approaches to encryption, so we'll do that first. There are two main approaches to encryption that you will see used within AWS and the real world in general. Each of these is aimed at solving a very different problem. First, we've got encryption at rest, and second, encryption in transit. Encryption at rest is designed to protect against physical theft and physical tampering, and a common example of this is a user with an encrypted laptop. So Nat's using her laptop as she would with any other device, but her laptop is busy encrypting or scrambling any data that it writes to the internal storage, and then decrypting that data when it reads it from the same storage into memory. Now there's a special piece of data that's used to encrypt and decrypt that data, and it's only known to Nat. Now the proper word for this is a secret. Now with laptop encryption, this is either the password for the user logging into the laptop or a piece of data that's derived from that. But in other types of encryption, it's more complex than that. What this means though, is that if Nat's laptop is stolen or tampered with, the data is encrypted at rest. Without the information required to decrypt it, it's useless to an attacker. If somebody steals the laptop without the passcode that Nat uses, all they have is a laptop with encrypted or scrambled data, which is useless. Encryption at rest is also used fairly commonly within cloud environments. Your data is stored on shared hardware, and it's done so in an encrypted form. Even if somebody else could find and access the base storage device that you were using, they couldn't access your data. Encryption at rest is generally used where only one party is involved, in this case Nat, and that party is the only person who knows the encryption and decryption key. The other approach to encryption is known as encryption in transit, and this is aimed at protecting data while it's being transferred between two places. So when Nat is using her internet banking, the data is encrypted before it exits Nat's laptop and decrypted by the bank when it arrives, and the same process is followed in reverse. So the bank encrypts any data that's destined for Nat's laptop, and Nat's laptop performs the decryption process. What you're essentially doing with encryption in transit is to apply an encryption wrapper, a tunnel around the raw data, and anyone looking from the outside would just see a stream of scrambled data. Encryption in transit is generally used when multiple individuals or systems are involved. So let's move on and talk about encryption concepts. In this part of the lesson, I want to introduce some encryption terms. Not all of these are immediately intuitive, and so if you haven't heard of these before, I want to confirm your understanding because I'll be using them throughout the course. Now we'll start with plain text, and this is a horrible term to use for this thing, because the name gives you the impression that it's text data, and it isn't always. Plain text is unencrypted data. It can be text, but it doesn't have to be. It can also be images or even applications. Plain text is data that you can load into an application and use, or you can load and immediately read that data. The next term is an algorithm. And an algorithm is a piece of code, or more specifically a piece of maths, which takes plain text and an encryption key, which I'll talk about shortly, and it generates encrypted data. Now, common examples of algorithms are Blowfish, AES, RC4, DES, RC5, and RC6. When an algorithm is being used, it needs the plain text and it needs a key. And a key is the next term I want to talk about. A key, at its simplest, is a password, but it can be much more complex. When an algorithm takes plain text and a key, the output that it generates is ciphertext. Now, just like plain text, ciphertext isn't always text data. Ciphertext is just encrypted data. So the relationship between all these things is that encryption, it takes plain text, it uses an algorithm and a key, and it uses those things to create ciphertext. Decryption is just the reverse. It takes ciphertext, it takes a key, and it generates plain text. Now, this is not all that complex at a high level, but like most things in tech, there are some details which you need to understand. First, I want to focus on the encryption key for the next part of the lesson. The type of key influences how encryption is used. So let's look at the different types of keys and different types of encryption. The first type of encryption key that I want to talk about is a symmetric key. Symmetric keys are used as part of a symmetric encryption process. Now, it's far easier to show you an example visually rather than just explain it. So here goes. Now, as everybody knows at this point, I'm a fan of animals, specifically cats. What you might not know is I'm also a fan of robots. And everybody knows that cats want to achieve world domination, and robots are working towards the robopocalypse. In this example, they've allied. They've created a plan for world domination. So on the left, we've got the cat supreme ruler, and on the right, we've got the robot general. Both leaders want to exchange data, their battle plans, and they want to do that without humans being able to read them in their plain text form. They need to ensure that the battle plans are only ever exchanged using ciphertext, so the humans never see the plain text battle plans. So step one is they agree on an algorithm to use, in this case AES 256. And they set to work preparing to send the plain text battle plans. Now the cat ruler, because he's the party sending the data, he needs to generate a symmetric encryption key, so he needs to create that and keep it safe. A symmetric encryption algorithm is used, and this accepts the key and the plain text battle plans. And once it's accepted both of those, it performs encryption and it outputs ciphertext, the encrypted battle plans. The encrypted battle plans are now secure because they're ciphertext and nobody can decipher them without the key. They can be sent over any transmission method, even an insecure way, to the robot general. The encryption removes the risk of transmitting this data in the open, so even if we handed the ciphertext over to an untrusted party and asked for him to deliver that to the robot general, that would still be safe because the ciphertext is undecipherable without the key. But this is where the problems start for our rulers. The robot general doesn't have the key which was used to encrypt the data. With symmetric encryption, the same key is used for both the encryption and decryption processes. So we need to find a way to get the robot general a copy of the key that was used to encrypt the data. So how do we do that? Well, we could transfer it electronically, but that's a bad idea because if the humans get the key, it's all over. They can also decrypt the data. We could arrange an in-person meetup, but for anything which is really sensitive, this is less than ideal because the people meeting to exchange the key could be intercepted on their way. We could encrypt the encryption key and then transfer that key. Now, that would be safe because the encryption key would be protected, but we'd still need to find a safe way of transferring the key that was used to encrypt that encryption key, and that gets really complex really quickly. This is why symmetric encryption is great for things like local file encryption or disk encryption on laptops, but not so useful for situations where the data needs to be transferred between two remote parties, because arranging the transit of the key is the problem, and generally we need to do that in advance so there is no delay in decrypting the data. If the data that we're transferring is time sensitive, the transit of the encryption key needs to happen in advance, and that's the most complex part of this method of encryption. Now, if we did have a way to transfer the key securely, then the same algorithm would decrypt the data using the key and the ciphertext, and then would return the original plaintext battle plans. But there's another way of doing it. and that's to use asymmetric encryption, and this addresses some of the problems that our rulers are facing. It makes it much easier to exchange keys because the keys used in asymmetric encryption are themselves asymmetric. Now let's look at exactly what this means. To use asymmetric encryption, the first stage is for the cat ruler and the robot general to agree an asymmetric algorithm to use, and then create encryption keys for that algorithm, which logically enough will be asymmetric encryption keys. Asymmetric encryption keys are formed of two parts, a public key and a private key. For both sides to be able to send and receive to each other, then both sides would need to make both public and private keys. To keep the diagram simple, we're going to use the example of where the cat ruler will be sending the battle plans to the robot general. So only the robot general in this scenario will need to generate any keys. Now a public key can be used to generate ciphertext, which can only be decrypted by the corresponding private key. The public key cannot decrypt data that it was used to encrypt. Only the private key can decrypt that data. This means the private key needs to be guarded really carefully because it's what's used to decrypt data. If it leaks, the battle plans could be compromised. The public key, it's just used to encrypt, and so the robot general uploads his public key to his cloud storage so that anyone can access it. The worst thing that could happen to anyone who obtains the robot general's public key is that he or she could use it to encrypt plain text into ciphertext that only the robot general could decrypt. So there's no downside to anyone getting hold of the robot general's public key. So with asymmetric encryption, there's no requirement to exchange keys in advance. As long as the robot general uploaded his public key to somewhere that was accessible to the world, then the first step would be for the cat ruler to download the robot general's public key. Remember, this isn't sensitive. Anyone can use it to encrypt data for the robot general, and that's it. That's the only thing that the public key can do in this scenario. So using the general's public key and the plaintext battle plans, the asymmetric algorithm would generate some ciphertext. The ciphertext can then be transmitted to the robot general, and once received, only the robot general could decrypt that data. This time though, there's no key exchange required because the rulers are using asymmetric encryption. The general already has his private key, and so he provides that private key and the ciphertext to the algorithm, which decrypts the ciphertext back into plaintext, and then the robot general has a copy of the plaintext battle plans. Asymmetric encryption is generally used where two or more parties are involved, and generally when those parties have never physically met before. It's used by PGP, a popular email and file encryption system. It's used by SSL or TLS, which is a system for encrypting browser communications. And it's used by SSH, a popular method to securely access servers using key-based authentication. Now, asymmetric encryption is computationally much more difficult to do than symmetric, and so many processors use asymmetric encryption to initially agree and communicate a symmetric key, and then this symmetric key is used for communication between those two parties from that point onward. Okay, so this is the end of part 1 of this lesson. It was getting a little bit on the long side, and so I wanted to add a break. It's an opportunity just to take a rest or grab a coffee. Part 2 will be continuing immediately from the end of part 1. So go ahead, complete the video, and when you're ready, join me in part 2.